So many of you are unfamiliar or have never been interested in why the periodic table looks the way it does. Most kids ignore the bottom or two separate rows and never realize that these rows, the F filling orbital area, actually fit in between the S and the P electrons. S and the D electrons, actually, that would be. This below is a fully expanded periodic table and a bunch of other periodic table examples below it. Look at how the S, P, D, and F, and even G orbitals, yes, there theoretically are G sublevel orbitals, would fit. There's also a video link right here where the periodic table could be much, much larger than we already know what it is. Quick watch from the Fun Professor guy as well is also available. Furthermore, at the bottom, we'll talk about paired and unpaired problem sets as well. First of all, here's the expanded periodic table. And you can see this looks a little bit different because this row right here is usually separate and it's down here. And you'll notice that it actually fits in this space right here. They're called the lanthanide and actinide series. And you can see that they actually lead off this series and go between the s orbital filling and the d orbital filling ones right here. That's where they actually fit. They're usually put below on a periodic table because otherwise the periodic table gets too long. And so it actually goes 6s2, then it goes to the 4 f's right in here, and then the 5 d orbitals fill right here. Usually it gets a little bit mixed up down in these areas, and you have a lot of exceptions, but that's where they normally go. And then you can see down here that they've actually shown it in a different way where they show an arrow right here showing the F's right down below it. And you can see a full expanded periodic table right here with all the elements put together with the F orbital filling right in the correct spot. Here's a full with G sublevel electrons. Now these haven't been discovered yet, but it's theorized that these exist from 119 on. And these would fit in between the F's and a whole bunch of F's that haven't been found yet, and the D's and then the P's over here. So this is a full G level orbitals as well. So knowing that those fit in between, when you write your electron configuration for these guys, make sure to fit that lanthanide actinide series in there. All right, the second question I've received a lot of are about paired and unpaired electrons. First of all, you have to know how to write your orbital notation, and that each box or each line is where you can put two electrons. The electrons pair up inside the box, one with an up spin and one with a down spin. That's a quantum number called the spin quantum number that indicates that the electron would go up or down spin and they pair up. Then the 2s orbital would fit two electrons as well. That would be spherical in shape. And then we'd have three 2p orbitals, one each a dumbbell shaped, and one electron would go in each before it pairs up, and it always has to be the same spin or the same direction arrow. This would have three unpaired electrons. Three unpaired electrons in this energy sublevel right here, 2p. Notice this would have two paired electrons right here, and this would have a pair of electrons as well. So paired electrons have one up spin and one down spin. Unpaired electrons have electrons that all have spin in the same direction but are in separate orbitals. All right, here's a little bonus of some paired and unpaired electrons with some exceptions to the electron configuration. Chromium and molybdenum happen to be a group or a family on the periodic table that have exceptional electron configuration. Also, the precious metals of copper and silver have this. You can see right here is the element chromium. Chromium would normally have 4s2, and then it would go to the 3d, and it would have 1, 2, 3, 4, but one electron would be promoted into the 3d, so giving you 1, 2, 3, 4, 5, 6 unpaired electrons like that. So it's changed from 4s2 3d4 to 4s1 3d5. It's a more stable electron arrangement by having two half-filled sublevels like this rather than a filled one, and then this one is just absent one electron. It's an Aufbau principle exception, because this filling of electrons in the 1s2, 2s2, 2p6, 3s2 is called the Aufbau principle, and it doesn't follow the normal pattern. You can see right here, copper does the same thing. It would normally be 4s2, 3d9, but one electron is promoted into the 3d energy level here, so you end up with 4s1, 3d10 to have a filled energy level that's larger, and then one electron in the 4s energy level. Lastly, here's some orbital shapes. I've never seen the f-orbitals before, but there are 7 of them, and this is a 3D modeling of them. And then here is also the modeling of all of the orbitals, the s, the 3p orbitals. Notice the x, the z, and the y orientations. And then here are the d orbitals, 5 different orientations to those. One exceptional one right here that has a donut around the middle. And then here are the f orbitals, again in the same type of schematic diagram. You can see that one's got a double donut one there. Lots of exceptions and lots of special pieces that are pasted and posted and shared with you in a Google document as well. And then don't forget, you can link right here where you can watch a quick video on a much, much larger periodic table and what it would actually look like.